All right, that one. Okay, 3 p.m. Now we need to use the CB to account for the the moment gradient in the beam, but when you can only use CB to increase the strength when you have the beam that will not reach MP or the beam that does not have proper lateral support. Because if you can recall, if you brace the beam properly, it's going to reach MP, right? And your section will be completely destroyed because MP is as good as it gets. That it's the strength of the section. You cannot go beyond that. But when you have, say, the long unbraced length, your beam may suffer lateral torsional buckling before it can reach MP. But when your beam is going to suffer lateral torsional buckling, if the moment is constant, it's going to suffer very easily. But if the moment is not constant, like the cases that I just showed you, your beam will become harder to have lateral torsional buckling. And this behavior is reflected through the use of CB. And CB can be calculated by using this. I'll come back to this later on, okay? Now, that's a general idea of the behavior of the beam. But again, before we get into that, it's easier to start talking about the local buckling of the beam first. And again, for compression members, we divide the compactness of the element into just compact and slender. But for beam, there are 3 regions. So when we look at the flange, the slenderness of the flange itself, it may be considered as compact or non-compact or slender. So instead of 2 sets of behavior, we now have 3. So that means we are going to have 2 limits, right? Because we have 3 ranges. So there are 2 limits to divide the ranges into 3 zones. If the flange or the web slenderness ratio is less than LP, okay, your member can reach lambda p, I'm sorry, your member can reach MP without any problem. If some of the elements, either the flange or the web, has the slenderness ratio exceeds lambda p but not lambda r, you're going to have some buckling problem that will prevent your beam to reach MP. And when you have some of those, again, either the flange or the web that has the slenderness ratio way beyond LR, they are going to buckle in the elastic zone, which means it's going to happen very, very quickly. So the flange or the web will just pop, like that, buckling elastically, and then you have to stop loading your beam. And when you stop loading, either the flange or the web will go back to its original position. Say, oh, I'm okay, because that's elastic buckling, but the load carrying capacity of your beam will be very, very small. Okay, so we have 3 zones now instead of 2. And now, you look at this. Of course, we now have lambda p and lambda r for this. And right now, you see the limit is not the same as in compression members because the stress is not the same. In compression member, you have a uniform stress, but in the beam, you don't. So that's why the limits are different. But for the web, it's much higher, you see? Because the web now has both tension and compression. So it is very, very difficult to buckle. And that is why the limit in the web is so high, but not the limit in the flange. Okay? So, and for the hot roll section available in the market, we can safely say that the web is all compact, but not the flange. You're going to have to check the flange always, okay? And for the channel, I think channel, everything is compact. And now the limit will be different if you have the build-up sections, okay? Because again, of the residual stress created by the welding process, because you need to weld the flange to the web, or the web to the flange, how you look at it. So the limits will be slightly different, and that crazy limit is for a singly symmetric section, okay? And likewise, we have some more limits for the square and tube and so on. And the overall picture of the design will be like this. Oops. Okay, here we are. We need to check the compactness of our element first. But the way AISC categorizes the calculation is like this. You need to make sure how your web is first. Because if you have a compact web, you will have one kind of calculation. If you have non-compact web, you will have another kind of calculation, another set of calculation. If you have a slender web, you will have another set of calculation. So for me, it is best that we look at the design model like this. You're not going to see this in AISC specification. They don't write it like this. But this is my own understanding, and I think it is better. Clarify the web first. If you have the compact web, you go into one kind of calculation, one set of calculation. If you have non-compact web, you go into another calculation. And then when you have slender web, it's another. But remember what I just said a few minutes ago? For all the hot roll sections available in Thailand, all the webs are compact. So for hot roll, we are here. And that also means you will only have this and this when you design the build-up section. Okay? Like plate girder, for example. Because in plate girder, you don't need a compact web, because a plate girder, it's a very, very deep beam, right? So if you want to make the web compact, it's going to be very, very heavy. And it is not necessary. We don't need that. So good engineers will just leave the web slender. And we will take care about that later on. It's a waste. And if you make a web very thick, it's very, very heavy. And you should know that we don't gain the flexural strength by increasing the web thickness, right? We gain the flexural strength of the beam by increasing the flange. So to make the thick web for a very deep beam is not a very, very good idea. So that is why they have something like this. And when we clarify this, you just need to check whether your flange is okay, and then you check lateral torsional buckling. Two things. Very simple. So that's the flange thing. This is the general idea for the flange. So you can have the compact flange, which means excuse me, pretty far from myself. No, sitting is good, but if you sit like for 4 hours or so, your body will begin to feel the stress, right? There's a residual stress in my body, so I need to move a little bit now. Okay, so when this is the overall behavior of flange local buckling. If you have a compact flange, the slenderness ratio of the flange is less than lambda p, your beam will have the plastic behavior. That means your beam will reach MP. Now, if your flange is so slender, beyond lambda RF, your flange will buckle very, very quickly, and your beam will have the elastic behavior, and the stress will come down very quickly because this is a quadratic function. And somewhere in between, there is this inelastic behavior. Okay? I have to say this because plastic is true. Slender is true. This is exact solution coming from the plate solution. That is also true. We proved that with stress distribution. This is just the connecting point. Okay? So this is the overall picture of flange local buckling, depending on the slenderness ratio of the flange itself. The next is the overall behavior of lateral torsional buckling. Now we will compare this with the unbraced length. Okay? If the unbraced length is less than LP, this is the length for the plastic moment, right? You can reach MP. So if you can provide the unbraced length for your beam that is less than LP, you are guaranteed to have the beam to reach MP, for sure. And again, the solution that some guy came up long time ago by using calculus is this, elastic behavior. And this will occur when your unbraced length exceeds LR. Just a quick look. The difference between this and that, this is lambda. This is the slenderness ratio of the element, right? But this is the unbraced length of your beam. And somewhere between the elastic behavior and the plastic behavior is the inelastic one. So this line is just the line that connects two behavior together. Because the elastic one is based on calculus. The plastic one is based on a stress distribution. The inelastic one is just, the line connecting the two. Okay? And this, ladies and gentlemen, this curve is based on pure moment case. Meaning you will have this line when the bending moment diagram is constant. And when you don't have constant bending moment diagram, it means that you can raise this line by multiplying it with CB. CB can only be used with the lateral torsional buckling because it is about your beam carrying the moment. You cannot use CB to increase the flange local buckling, right? Can't do that. And this, you can raise your load carrying capacity or moment in this case as much as you want, but no matter how much you raise this, you cannot go beyond MP, which is the natural boundary of your cross section. Okay? You cannot use CB and then, my beam can carry moment way beyond MP. We're not Harry Potter here, so we cannot do that. Okay? Even Harry Potter cannot do that. And again, this limit here is not MY. Notice that this is MR. It's a residual stress moment. I don't remember how it stands for, but this is based on residual stress. And MR is basically 70% of first U of MY. Okay? So this is the overall picture of the behavior of the beam. Is there any question, ladies and gentlemen? Pretty easy, right? Okay. So just to look at the lateral torsional buckling, that's it. It's a very famous picture. If you type lateral torsional buckling, this is the first picture that comes up on the internet, I think. It's pretty classic. I think what happens here is that, see, there's some kind of concrete portion over there. They pour the concrete onto this first, but this beam has no bracing. So when you have the concrete on one side, it creates torsion. It just like that. This is my guess because it seems like it. Okay, crazy. Yeah. Now, let's go with the first one first. I think we're gonna have another break at 4 p.m. right? Okay, so a pretty long time. So okay. This means you have to clarify first that your web is compact. Okay? Here's a note says here. It is imperative. It means urgent and important. So it is imperative that web is confirmed as compact. And you have when you have the compact web, the next thing you need to do is to check your flange. Okay? If your flange is compact, your nominal moment will be equal to MP. If your flange is so slender, your nominal moment will be equal to this. Whatever that is, 0.9 multiplied by the Young's modulus and Kc and elastic section modulus divided by lambda square. Lambda is just the slenderness ratio of the flange. The BF over 2TF. Kc is based on the slenderness of the web. Wow, the slenderness of the web affects the flange local buckling. Okay? And somewhere in between, to connect these two behavior is the equation for the inelastic behavior. And if you look at this one, ooh, I need to get up. Need to walk a little bit. Oh, okay. Need to change the posture. If you look at this, what do you want, sir? No, I don't need help. You can carry me if you want. You look at this equation. You see, this is basically y equals C mx plus b, that sort of thing. This is the slope of this line, right? This is dy by dx. Because if that's mp and that is this is mr, which is equal to 70% of the first yield. So mp minus mr is this, and this is lambda r minus lambda p is that. So this is basically dy by dx. Oops, that happens a lot. It came from the previous line. I don't know how to remove that. Anyway, so this becomes a slope, and this tells you where you are in the x ordinate. Right? So this is the ordinate x. So when you know x, you know y. So the equation itself, it's just the linear equation that connects the two behavior together. So there we have it. That's it. Piece of cake. What's so difficult about it, right? What's so difficult about it? I don't know. Okay. The next one, now we look at the lateral torsional buckling. Again, it's pretty much the same. If your unbraced length is less than LP, you're going to reach MP. You can destroy your beam if you have LB or unbraced length less than LP. And if your unbraced length is greater than LR, you're going to have this. Woo! Exact solution from calculus. Can you believe that? They used L'Hopital to solve this, you know? I don't want to go back and study this anymore. Just whammy. So every time you see pi, you know right away this must be something with differential equation. And yes, it is. Crazy, but true. So believe it or not, exact solution. And again, see, the form of the equation is similar. dy by dx, and this is the delta y, and it gives you the coordinate. I'm sorry, this is the delta x, so it gives you the coordinate in y, right? But the major difference is that now you have CB here and here. It doesn't take guts to use CB, you know. It's just the factor that reflects the true behavior of our structure. So I don't know why there's that idea circling amongst engineers. Just use CB equal to 1 to be safe. But if you use 1 and the value is 1.67, just my case, for example, you're losing 67%. It's like, hey, I'm going to give you a salary 100,000 baht, but it's fine. Maybe you could actually have 167, right? K for your salary, but no, we're going to use it. I can just give you 100,000. Are you okay with that? You're losing 0.67 for your salary. I'm fine. I don't need that much money. I'm fine. Can we do that? You rather not, right? But for this, let's just keep the strength somewhere for 67%, for example. You don't want anyone to store your salary for you, right? Just the same here. Oops. We go again. It came from the previous slide that I made a long time ago. Oh. Okay. So, again, we can use CB. And the CB can be as much as 3. We don't go beyond 3, I suppose. It's just some recommendation somewhere. But the more the moment fluctuates, you know, the change the value in your beam, the greater the CB you're going to have. Because the more the moment fluctuates, the beam becomes harder to buckle. Right? And you feel that if the moment is just, you know, there's just positive and negative moment that, because when you have the positive moment, your beam will buckle on top, right? Because that's where compression is. And when you have the negative moment, your beam will buckle at the bottom. Keep that in mind, ladies and gentlemen, because remind me in the next few seconds that I need to talk about the bracing. Okay? But so that means when you have the moment coming up and down, positive and negative, your beam will buckle sometimes on top, sometimes on the bottom. So it becomes very, very difficult for the beam to buckle. And it should be reflected on the value of the CB that we use. So this is the one major problem why not many people want to use steel, because they don't understand the behavior and they don't use the maximum available capacity. And if you don't use CB, it means you end up having a section bigger than it has to be. And when you have the section bigger than it has to be, it looks ugly and it becomes uneconomical. And this is one major obstacle that we need to overcome. Because, you know, every time I talk about this in the lecture, and I jokingly ask, how much do you use for CB? It's 1, right? And then people laugh because, yeah, they use 1. and you know, the last time that I used the computer program is that the computer program will ask you how much CB you want to use. It doesn't automatically calculate that for you. And not you, because you're not going to do it, right? But many engineers just automatically CB 1, 1, 1, 1, 1. And, you know, they're going to end up with the structure so huge. Okay? But don't forget, you can't go beyond MP. Okay? there is always, for lateral torsional buckling, this, to cap off your maximum capacity. Okay? And in some cases, like the cases that I had, CB was so large that I could, have the flexural capacity up to MP anyway, even though my unbraced length is so large. And I was not afraid to use it. But it still stands today. It's fine. Okay. Any question, ladies and gentlemen? Now, back to bracing. As I just mentioned a few seconds before, only compression can cause buckling. Please, if you think tension can cause buckling, I think you can fly before tension will cause buckling. Because it will not happen, right? How can tension cause buckling? Not on this planet. I don't think so. But compression causes buckling. So that means when you are dealing with the beam, you need to brace the beam where compression is. Do you agree? It's a common fact about the behavior of the steel, right? If you brace the tension flange of your beam, what good does it do? Oh, tension is going to dance? My tension flange is going to dance? No, your compression flange is going to dance. So you have to brace your compression flange. So for example, if you have, let's say, the beam here somewhere. If you have the beam, it doesn't matter what the load is, but let's say it's a fixed support here maybe. So your moment diagram looks like this. It's a negative moment here, right? Say if you have negative moment here. And it's so large maybe. Whoa, like that. Somehow, you have only a small positive moment here. You have a lot of negative moment here. You say, oh, I need to have some bracing, so let's brace it here. Does that help here? No, of course not. How can it help? Because your compression is here, right? This is understanding the beauty of the behavior of the structure. It doesn't matter if you don't understand the behavior. The calculation is a piece of cake. You just substitute numbers in the formulas. But if you don't understand the behavior, how do you know when to use which formula? Right? So everything should come from feeling the structure first. Feeling it, knowing how it is going to dance for you, and then design accordingly. All right? So like this case, if you have a beam like this and say, okay, you have some maybe small beams coming in on top, this will not help. It can only help when you provide a kicker coming down to stop your compression flange from moving. Right? And that's the idea. And now we are talking about the brace. Let's not forget that the behavior of the beam under moment is called lateral, torsional, buckling. That means both of them have to happen at the same time. In English, we use the word simultaneously. It's a beautiful word. That means at the same time, right? So they have to happen simultaneously, which means if you want to provide bracing, you can stop either one of them, and the lateral torsional buckling will not occur. If your beam cannot move laterally or torsionally, the lateral torsional buckling will not occur. And that is why, ladies and gentlemen, when you have a simple beam with the concrete floor on top of it, and somehow you connect your concrete floor to the top flange of the beam, which is compression flange because it's a simple beam, right? Your beam will be fully braced because compression flange cannot move. And in that case, you will easily reach MP. Okay? The most important thing is to understand the behavior. And this will follow. Oops, I mean this. That will follow with clarity because you know where you're going, because you can see the behavior, you know where your beam is going. All right? Any questions, ladies and gentlemen? Pretty crystal clear, right? Crystal clear. Mm-hmm. Wow. And please keep in mind that many of the values shown here are the properties of your section. And I have made this available in the steel table. The J, the S, the H naught, the RTS, they're all available in the table. Okay? And I think LP and LR as well. So if Kun Tam did not forget to include that in the table at the back of the book, you should have all these values available to you. Okay? If not, you can just calculate those values by yourself. LP is that, LR is that, RTS is that, CW is that, blah, blah, blah. Okay? So that is the basic idea of the design of the hot roll section. Now we're gonna get into the build-up territory. So if you have no use for it, and if you're not interested, I can just go over it quickly. Okay, because this is almost 4 o'clock. And actually, what is the timetable, the actual timetable for us? We should, the session should end at like 5, maybe, right? Yeah, but it's almost 4, and we are just, I have only 60 slides left. Huh? This is already 3:45. So you want a break now? Yeah, it's good. You want to have a break now? Yeah, good. Please. Yeah, I'm tired too.